Print out the other part. Okay. Okay, so we talked about this on Friday, right? Or Thursday. That it had been reposted on Canvas, but that you needed to print out the end of it. Okay. So we all freaked out on Thursday. I told you guys where you could get it. Some of you went and got it. Some of you didn't. It doesn't matter. Okay. You can do whatever you feel is necessary for yourself. You can get it later and do it like that. So multiple things happening. So how hard is it for me to take a die and roll a 6? What's the probability of that happening? 1/6. Okay. What if I want to roll a 2? What's the probability of that happening? 1/6. What if I want to roll a 6 and then I want to pick up the die and then I want to roll a 2? What is the chance, okay, that I get a 6, then I pick it up and roll again and I get a 2? Okay, 1 out of 36. All right, and the idea is, notice that the probability went lower, right? It was hard enough for me to roll a 6, 1 in 6 chances. Now to roll a 6, pick it up, and then roll a 2, it's getting more difficult to do, right? So you're basically taking that probability and multiplying it by the other probability, because probabilities are smaller than 1 unless there's 100% of them happening, then they're 1. So every time you multiply together numbers that are smaller than 1, what happens to them? They get even smaller, okay? So for something that's more difficult to obtain, it makes sense for us to use multiplication in this sense, because multiplying two numbers smaller than 1 together makes a smaller number, and it makes sense that it would have even less likeliness of occurring if you had to do multiple things in a row, okay? So basically we multiply them, okay? If one event depends on the other, you might have to adjust what you're multiplying, and we'll see different scenarios where we would do that, okay? All right, so you're at a bowling alley. Some random examples with coins and stuff like that. My advice, don't just copy it down. All these formulas are in your books, okay? They're on the note guide if you go home and get the note guide. I would just write down which example number and fill it in like that, okay? All right, so you're at the bowling alley, okay? There's 5 black and 3 green bowling balls, okay? One customer selects a bowling ball, and they put it back because it was too heavy, and then the next customer comes up and selects a ball from that same shelf. Okay? What's the probability that each customer picked a green bowling ball? So, first customer walks up. What's the probability they pick a green bowling ball? Ashley? 3 out of 8. There are 3 green ones out of 8 total. That's how we calculate probability. Right? Did they keep it or did they put it back? They put it back because it was too heavy. Okay? So they put it back. So the next person comes up. Is their choice independent of the previous choice, or is it dependent on it? Independent. Because the situation hasn't changed, because the person didn't keep the bowling ball. Okay? So what's the probability the second person picks a green bowling ball? 3 out of 8. But the chance that one did this and then the other one did this is less than 3 out of 8. It's what you would get when you multiply 3 out of 8 times another 3 out of 8. And so it would be 9 out of 64. In that same scenario, if the first person did not put the ball back on the shelf, how would our calculation change? Ashley? Good. The first person still has all the balls to choose from because they're the first person to approach the shelf. But if they kept the green ball, the total number of bowling balls has now gone down to 7. And the number of green ones has been adjusted to 2. So the second person's chance of picking a green one is now 2 out of 7. Okay. Or this will give us 6 out of 56, which reduces to 3 out of 28. Okay? Is that okay for that idea of multiplying them? And does it generally make sense why we'd multiply it and get this smaller number? Okay? All right, this is the same but with quarters, so we're good. Let's skip that one. All right, and we'll look at this one. We'll look with cards because cards are a little bit more difficult for you guys. All right, so you have 52 cards. 3 cards are randomly chosen. They are a 10, a jack, and then another 10 in that order. Okay. The first part says they happen if the cards are replaced after each selection. So, to pick a 10, what's the probability? Good, Kenny. 4 out of 52. Okay, there's 4 10s in a deck of 52 cards. You put it back. The next card needs to be a jack. What's the probability of drawing a jack? There are 4 jacks in a deck of 52 cards. Okay, and then you put that back, and now you have to draw a 10 again. Okay. Again, the chance of that happening is 4 out of 52. Because you want these 3 things to occur in a row, you would multiply those 3 things together. Okay, and we're going to trust that you guys can multiply and reduce through it. Okay, you can reduce before or after. What would be the difference in the second calculation if the only difference is that we're not replacing the cards? See, Ashley, but she helped me with the last one like this. Michelle. Okay, so somebody explain to me why the denominator is decreasing by 1 each time. Andrew. Good, we're keeping a card. So the new probability is calculated with a new number of cards because somebody didn't replace the card back in the deck. Someone explain to me why it's a 4, and then a 3 in the numerator. Ben. Good. So there's 4 of each type of card, but because you kept this one out and you already chose a 10, there's now only 3 10s left in the deck. Does everybody understand how we would adjust the probabilities? When they're independent, they don't need adjusting because each time is like a new situation with everything there. And when they're dependent, when you're keeping stuff out, the numbers will adjust. Okay? Are we good with those calculations? Okay. And again, trying to get more and more things to happen in a row becomes less and less likely, right? That's why the denominator gets really big and the probability overall is getting much smaller. Okay? All right, so then what if they say, what if I go to roll a die, okay? We already talked about this. The chance I roll a 6 is 1/6. The chance I roll a 2 is 1/6. What if somebody tells me I'm a winner or I've achieved my goal if I roll a 6 or if I roll a 2? So what's the probability I win, okay, or get what they wanted? Kenny? 1/3. Are we okay with that? Because I had a 1/6 chance, but they're also letting me get this other thing that was also a 1/6 chance. I now have more likelihood of getting an outcome that they want because they gave me more options. Does that make sense to everybody? So when they say you can do this or you can do this, we add the probabilities together because when you add 2 numbers together that are between 0 and 1, once you add them up, you get something bigger than either one individually. Okay? And when they're saying or, they're saying you have more ways to win. So the likelihood should increase that you win, or the probability should be bigger than what it was of any one individual event. So what we have to be careful of here, and we saw this a little bit last time, and so we'll look at it, is if they're mutually exclusive or not. This first example is mutually exclusive. It says find the probability of drawing a jack or a queen. What's the probability you draw a jack? 4 out of 52. There's 4 of each type of card in a 52-card deck. What's the probability you draw a queen? 4 out of 52. Now they said you can do either. Okay, so they've increased your likelihood of getting what they want. Okay. So here's the chance I draw a jack. Here's the chance I draw a queen. Because they said I can do either, I get to add those chances together, and I get a bigger chance that it will happen or something more likely to happen. So this becomes like 8 out of 52, okay, or 2 out of 13. Now, this is mutually exclusive events because the events cannot overlap. When I pick a card out of that deck, is there a chance that it is a jack and it is a queen? No. That's why these events are considered mutually exclusive. If it was a jack, there was no way it's a queen. And if it was a queen, there was no way that it was a jack. Okay, so that makes our calculations simple. Okay? But what could happen, look at this problem, it's only slightly different, and the formula just has a little bit of subtraction at the end. Okay? This problem says, what's the probability of drawing a queen or a diamond? Why is this not considered mutually exclusive events? Lauren. Good, I could have a queen of diamonds. So when I count all the queens, am I going to be counting the queen of diamonds? Yeah. When I count all the diamonds, am I going to be counting the queen of diamonds? So you said, I'm going to count it when I count the queens. I'm going to count it when I count the diamonds. Is that card really in there 2 times? No, but you just counted it 2 separate times, right? So do you remember the dice problem that we did on Thursday where we circled the rows? Okay? And getting a 5 and the red one getting a 2 or something like that. There were 6 ways for each of them, but one of those ways overlapped, and so we extra counted it one time and we had to subtract it back. That's the only difference here, and that's what's happening. So I say, okay, the probability of getting a queen is 4 out of 52. Because it's an or, I have more likelihood of doing what they want me to do because they're giving me this second option. I'm going to add that probability with the probability of getting a diamond, which is 13 out of 52. But because these things could occur at the same time, I have overcounted. Okay? And basically, I've overcounted. Notice in the formula it says subtract the probability that it was A and B. So in our problem, we overcounted by the number of cards that are a queen and a diamond. So I want to subtract however many cards out of the 52 are both a queen and a diamond. And so how many is that? There's just one queen of diamond card, right? So I'm just going to subtract that 1. Because I still want to count it, I just want to only count it once. And what happened was I counted that 1 card here, then I counted that 1 card here. I counted it twice. So I'm subtracting one of those times so that I just count it the correct amount of times. So this is 16 out of 52, or 4 out of 13. Okay. Yeah, Kenny.
If we were doing this on the test, we just went straight to 3 over 52 plus 13.
Yeah, I might ask you how you knew it was 3 if I'm not understanding, but yeah, that's fine. Okay. Is this all right with everybody? So, and we multiply because they're saying you have to do this and you have to do this, and they're making it hard to succeed, right? So the likelihood of that happening and then that happening and then that happening starts becoming less and less, okay? So the multiplication makes the denominator grow, but the overall fraction is getting smaller and smaller. If they use or, we're adding them because you could do this or you could do this, meaning they're making it easier for you to have successful outcomes. And when we add numbers together that are less than 1, okay, we're getting closer and closer to 1 or a better likelihood of it happening. Okay.
What if you put the card backwards? Would it then make a chance to draw?
Well, in this one we weren't counting. Usually you do it with and because this was an or, so you're only picking 1 card. But they're saying it could be this or it could be this. Is that okay? Yeah. All right. So in example 7, we're not going to necessarily do it, but just to understand if we have to subtract it. So the question says, what is the probability that it is a quarter or a nickel? So without reading the rest of the question, I'm thinking addition, right? Because I can win multiple ways. I can draw a quarter or a nickel, okay? Or I can be successful multiple ways. So I have a better likelihood of succeeding, okay? Because they're giving me 2 options. The next thing is, are they mutually exclusive? When you draw that coin out of the bag and you look at it and it's a quarter, could it also be a nickel at the same time? No. Okay? If I pull out a nickel, I see that it's a nickel. Can it also be a quarter? No. Nickels are nickels and quarters are quarters. They aren't interchangeable in our monetary system, right? So, in example 7, am I going to have to subtract anything when I go to calculate the probability? No. Because it's this. I calculate the probability of quarter, probability of nickel, add them together. There's no overlap. Now, in example 8, they surveyed 300 people. 134 said they would recycle aluminum cans. 108 said they would recycle glass. Of those people, 62 said they would recycle both. So if you select a person at random, what's the probability that he or she would recycle aluminum or glass? Okay? So, you're picking a person at random. You're using these survey results as kind of your probability that it will happen, right? So, what's the probability that someone says, yes, I'll recycle aluminum according to the survey? How many people said they would recycle aluminum? 134. Out of how many people surveyed? 300. Or, okay, glass. So how many people would I expect to say, yeah, I'll recycle glass according to this survey results? How many people said they would recycle glass? 108, right? Out of how many people surveyed? 300. Okay. Now, mutually exclusive or not? In other words, did I overcount or not? So, are there people that answered yes to both of these questions? Yes. Okay. That means that when I was counting the 134 people that said, yeah, I'll recycle aluminum, some of those people are the same people that said, yeah, I'll recycle glass, and I just counted that person as two separate people by putting them in each category. Okay? So I still want to count them. I just don't want to count them in each category because I've counted them twice. Right? How many of these people were there? 62. So there are 62 people that are in this category and this category that I overcounted. Okay? Let's see. 230, 242. So 180 out of 300? Or 3/5? So basically, this whole mutually exclusive idea is just make sure if you're adding up these different scenarios, you're not counting the same person or the same individual thing here and here again, because then your probability is going to be too good. Okay, it's going to look too good because you've overcounted how many of those people there really are. Okay. All right. The last thing that we're going to look at is something that's called binomial probability. Okay. They use something called the binomial theorem. You'll see it. And you guys have done combinations. So it basically counts up, okay, we're going to do this many things. What's the probability that this many of them turn out the way we want? Like that example 9 up there. What's the probability of getting exactly 3 heads if you do 5 coin tosses? Well, you might think, well, that's fine. Like, well, exactly 3 heads gets a little tricky. A head is 0.5, right? Or half is the probability of obtaining that. So that has to happen 3 times, but then twice I have to specifically not get a head, which means I get a tail or whatever. And then there's the probability of that, which for flipping a coin, there's real nice, right? Half and half. Okay. And then there's like, well, what if it went head, head, tails, head, tails? Or head, 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 tails, tails, okay? So instead of writing out all those different things and trying to calculate them separately, the combination kind of counts the number of groups for you, and then the stuff you see after it with the P's and Q's takes into how many things you need to end up being heads and how many things that you don't need to end up being heads, okay? So this is the way it would work. So right now, just notation-wise, we're trying to get 3 heads in 5 tosses, or the language they use in the formula is trials, okay? So small side note for a minute, okay? So probability that I get a head, and then another head. What's the probability of flipping a head? 1 out of 2, right? A half. And I get another one. So what am I going to do with the 2 probabilities? Multiply them together, and the next probability of getting a head is a half, okay? And then I get another one. So now I'm going to take this multiplication problem and be multiplying it by yet another 1/2. So to calculate the probability of getting those 3 heads, a half times a half times a half, right? The probability of a head, but multiplying itself 3 times, because that's how we would calculate getting it 3 different times in a row. Is that okay with everybody? Right? So that's this part of the formula right here that says P to the R power. Notice it says P is the probability of success. For us, a success is getting a head, and the probability of getting a head is 1/2. We need to get 3 of them, so it's to the 3rd power. That's like the R in the formula, okay? Because R is the number of successes that we're trying to get. So does it make sense to everybody why we would raise 1/2 to the 3rd power if we were trying to get head, head, head? But how many times are we flipping the coin? 5. And do we want to get another head? No. Which means the other 2 flips have to turn out how? Tails. Okay. So it's not only that I needed to get a head and a head and a head, I now have to get a tails and a tails. Okay? So what's the probability that it's tails? A half. Okay, but how many tails do I need to get? 2, so a half times a half, right? So that's where this part is coming from. Heads and tails is a little silly because their probabilities are the same. But notice up here, so the Q is what's the probability you didn't get what you wanted. Okay, and heads and tails, they're the same, but if we were doing something with different likelihoods, it would be different. And notice the exponent on that says n minus r. N is how many things are you doing minus the number that you want successful. In other words, we're flipping the coin 5 times. We want 3 heads. How many of this other thing do we want? We want 2 of them, and that's coming from 5 minus 3. There's 5 things. I want 3 of them to turn out the other way, so there's 2 left to turn out this way. Okay? Now, this counts heads, heads, heads times tails, tails. But would they have to come in that order? No. Okay? I could have heads, heads, tails, heads, tails, head, tail, tails, head, head, right? So we could sit here writing out H's and T's and see how many different ways the H's and T's could turn out. Okay, so remember, we used combinations and permutations to count those things, right? Here we're going to use a combination because are we going to be able to tell the difference between the way the H's are ordered? No. One H is an H. You're not going to be able to tell if it was different than the one next to it. So that's why our combination is going to come in. So it's going to just count the number of ways you can group the heads and tails. Okay? There are 5, and I want 3 of them to turn out heads. So it'll count the number of ways from 5 things you can pick groups of 3 heads. So it'll take this probability and say, oh, yeah, that's the probability, but it also shows up here and here and here. It'll multiply it by that number of times. Is that okay with everybody? So it's kind of a crazy-looking formula, but all it's doing is saying I need this many of these probabilities times this many of these probabilities for each outcome. And because they could occur in a different order, this will count the ways that I can group them. Is that all right? So this is in your stats project. You guys write one problem like this. Okay? So it could be about heads and tails. You could survey people and calculate a probability. For example, let me show you this one. Okay. In the month of February, at a ski resort, the probability of snow on any day is 1/4. Okay? What is the probability that snow will fall on at most 2 days of a week-long trip to that ski resort in February? Okay? So there's a couple things going on here. First, the probability of snow on any given day was how much? 1/4. Okay? And for us, this is our P. That's the probability of our success, snow, right? We're counting snow is what we're counting up. But that means the probability of no snow on any given day is what? 3/4. How did we get that? It's either snowing or it's not. So if the chance that it was snowing was a 25% chance, the chance that it's not snowing is the other 75% to make a 100% chance, okay? So 3/4. And this is like our Q, okay? The not successful probability. Okay? The second thing that's going on here is the language. At most 2 days of snow on a week-long trip, okay? What does it mean to have at most 2 days of snow? What options does that give us, Danny? 2 or less, which means for us there could be 1 day of snow or there could be 2 days of snow. That makes this one of those or probability problems, right? I want to calculate the probability of just 1 day of snowing. I also want to calculate the probability of 2 days of snowing. Those 2 things would both be successes in my problem because they would be at most 2 days. Kenny? Oh, yeah. And we can calculate the probability of 0 days snowing. Thank you. Was that your same point, Ashley? Yeah. Good. So we're going to calculate the probability of 0 days of snow. We're going to add it with the probability of 1 day of snow. And we're going to add it with the probability of 2 days of snow. And then I'm going to stop because that's at most 2. This is success, this is success, this is success. 3 scenarios on my trip that could happen that I would consider success. Okay? Now what's the probability of each of them? So 0 days of snow. Out of how many days are we talking about? 7 days. Okay? So, because I have a snow and not snow probability, I can use this binomial probability. So the chance that there's 0 days of snow is a 7C0. And then I say, okay, what's the probability of the snow coming? For every day it was 1/4. And I'm hoping that that will happen 0 times in this scenario. And the not snow is 3/4, and I'm hoping that will happen 7 times. Okay? But I'm good in this other situation too. Can somebody tell me what it's going to look like for 1 day of snow out of 7? What's that probability calculation going to look like? Michelle?
Is it 7C1 times 1/4 of 1 power?
Good.
And 3/4
To which power? Good. Okay. Notice that these powers are always adding up to the number of days or the total number of things, right? Because you want part of them to turn out one way and part of them to turn out the other way. Okay? All right, someone new. What would it look like to use this idea of binomial probability to calculate this third option? What's the probability that we get 2 days of snow? Yeah.
would do 7C 2 times 1/4 to the second power times 3/4 to the fifth power.
Good. And then we would go ahead and add that all up, and we get some decimal less than 1. That would be our overall probability. Is that okay? So this problem had 2 ideas from it, 2 ideas from today in it. One is how to calculate this binomial probability. Okay, and it's binomial, right? It's when you have 2 options. It's happening or it's not happening. Okay, and you have the probability of both of those. Then you can use this idea. Okay, and it's how many of the total do you want to happen, and then you go through the calculation. The other idea that was in play here, though, is because they used the language at most 2 days, they gave us options. No days, 1 day, 2 days. And so we had to do each of those probability calculations separately and then add them together. Okay? Is this all right with everybody? Yes? All right, I'll let you guys start working on your homework. We don't have to do the last. Kind of repeats what we just did.